Okay, so it'll go from, these are chapters 8 through 10 in your book. So if you, like in the textbook, so you know where we're at, because you will do some problems from there. There's 12 chapters for the AP statistics, and so we finished the 7, and then chapters 8 through 10 kind of all bunched together into this one big topic of confidence intervals and significance tests. So this will be the first one. So the very first thing that we're going to look at is a one proportion confidence interval. Now I'm going to show you on your calculator, and I'll pull it up here as well. On the calculator, there are a whole lot of different intervals and tests that you're going to learn in the next 13 days. Okay, so if I go to, on my calculator, if I go to stat and I go over to test, in no other class should you probably have ever done that, but in this class, this is where we're going to basically be living the next couple weeks, is in this menu. So if you go to stat and you go over to test, you're going to see all these different types of tests that you've never heard of, but you do know of something called a z-score. So there's a z-test. There's also a t-test, because there's going to be a t-score. There's a two-sample z-test. When you have two things you're talking about, there's a two-sample t-test. So you see 4 things there. Those all deal with means. Then we're going to talk about proportions. We have a 1 proportion z-test, a 2 proportion z-test, a z-interval, a t-interval, a 2-sample z-interval, keep going, a 2-sample t-interval, a 1 proportion z-interval, and a 2 proportion z-interval. If you notice, proportions only have z. And so those are the ones where you know what type of test you're running. The ones with mean, when you see 2-sample or you see z or t, those deal with the mean. So when we're talking about proportions, we are going to be in either 5 and 6, which is either a 1 proportion test or a 2 proportion test, or down here in A and B, a 1 proportion interval or a 2 proportion interval. By the time we finish this unit, we will have gone through all the way to B, okay, to letter B. Now, when we get to the next unit, it talks about what's called chi-squared, and that is the one that looks like an x squared, but it's not an x, it's chi-squared. There's 2 tests to learn for it, and then in the very last unit, we skip over this one. This one we do not do in this class, but in the very last unit, there's a linear regression test. Just tells you if your data is linear or not. So all of these on here, all the way 1 through 0, so there's 10, 11, 12, 13, 14, and then a 15th. You'll know 15 different types of either intervals or tests. They'll be split up into different ones by the end of the semester. So that's where we're going in the next about 20 days. Okay, so today where we're going to be, and as you learn one, they're going to get even easier. But today, where we're going to be is in letter A. It's going to be the 1 proportion z interval is where we're going to go whenever it's time. But that's what we're going to be looking at. We're going to be looking at intervals that have just 1 proportion. So that's where we'll be on our calculator. So I just wanted to give you a preview of that. Okay. So 1 proportion confidence intervals, couple things that you need to know. First of all, you need to know what the interval actually looks like. So we use this, there's a reason for this. We use this to estimate the population proportion. So that's why I gave you a big space here to write all this in. You can use a 1 proportion confidence interval to estimate the population proportion of whatever you're talking about. So it's just like what we were doing before, where we're taking a sample and we want to take our sample and use that sample to estimate the population. Now, all of these have a formula. That formula is, I'll show you where it's kind of connected on the formula sheet, your AP Stats formula sheet, it's on there. But here is the formula. It is p hat plus or minus this. You'll see what this is in a minute. Okay. So p hat is your, this one is called, this is your estimate, right? This comes from your sample. So this is the estimate from your sample. So like, if you took a sample and 30 out of 100 people said yes, then your p hat would be 0.30. It would be 30%. So that always comes from, what was my sample? How was my sample? This is a z-score. This comes from our confidence level. So how confident we want to be. And we'll talk about the different ones in just a minute. Okay, the z-score comes from our confidence level. A z-score, typically, we talked about is like how many standard deviations you are away from the mean. It's kind of going to be the same way. If you want to be more confident, then you're going to have to use a different z-score. If you can be less confident, you can use a different z-score. So it just depends on how confident you need to be in your results. And then the last part, that square root of p times 1 minus p over n, that is your standard deviation. Okay, so, and you should have seen that before. So that's standard deviation for a proportion. So we've actually done that in some of these before, which is the good thing. When you see the standard deviation for a mean, you'll say, oh, we did that before too. So some of these are kind of repetitive things that you've seen in the chapter 7 on sampling distributions, because it was setting you up for chapter 8, 9, and 10. Okay. The other good thing is once you learn how to do a one proportion confidence interval, then tomorrow when we do a one proportion test, it's going to kind of be a lot, you're already going to have the formula, so it's going to kind of make more sense. All right, so we need to talk about some common z-scores, because these are in there and you need to know some very common z-scores. So these are common, I'll write this down below. These are common z-scores. It's typically how confident like we want to be that you see in a textbook or in a problem. Typically, you're wanting to be 90% confident, 95% confident, or 99% confident. Okay? So we typically, those are the ones that your book usually uses. If your book does not say how confident you need to be, so if your book doesn't say 90, 95, or 99, it's automatically, by default, it's automatically going to be 95. That's like the default. If for some reason the problem doesn't say how confident to be, 95% is the default, right? That's what it's going to be. All right. So there is a way to calculate these. So the 90% confidence interval is, we should memorize them, but I'm going to show you kind of what they are as we go through. So 90% is, to be 90% confident, basically I'm going to draw a little curve and show you what it looks like. To be 90% confident, you want your 90% to be right here, which means how much is in each little tail? 5, right? So there's 5% here and 5% here where you would not be confident in, right? To be 95% confident, I'm going to draw another little curve. You want 95% to be in the middle, and in each tail there's going to be how much? 2.5. Yep, 2.5% where you're not confident down below, and 2.5% up above. And then the last one is 99%, and what's in each tail? 0.5. Yeah, just 0.5%. Okay. Now, so there is a way on the calculator to get these, but the best way is just to memorize the numbers eventually because you're going to use them so much and so often. So let's go and see how we get these numbers. So the 90% confidence interval is, you're doing the 90% confidence interval, and I can make this smaller. Then you're going to go to your calculator and you're going to go to second vars, and we're going to use inverse norm, which we've used before. Now, the area is the area to the left of where it ends. So my the confidence level, it like ends right here, okay, on each of these. So the area always does the area to the left anytime like you want to know that. So for 90%, the area to the left of that line is actually 0.95, okay? Because it's that 90% and the 5% that were unconfident. So to find the 90% z-score, you actually put in 0.95. A lot of people think, well, that would be the 95% z-score. No, it's the area to the left of that last line.
Why does mine ask me about scale?
It doesn't, just say left. So it'll be 0.1, it's 1.645 is what we use for the 90% z-score. Okay? That's how much we round it to. 1.645. That's the 90% z-score. So we go from the end there to the left. Now, the 95% z-score, what would we put in for area?
97.
Yep, 0.975. So from the end of my confidence all the way to the left, so 0.975. That gives you 1.96. So that's what you'll put for the second one. And then for the third one, you would put in 0.995. And that's going to give you 2.576. So for 95%, it's 1.96. For 99%, it's 2.576. If you remember way back in chapter 2, for the normal distribution, we said if you're one standard deviation away from the mean, 68%, 2 standard deviations is 95%, and 3 is 99.7%. Remember, 2 standard deviations is 95%. That's what this is. It's right at 2 almost, the 95%. So these are 3 numbers, okay? Whether you understand how it's calculated or not, I just wanted to show you. But there's 3 numbers that are in that formula that you're going to see. So a lot of the problems are going to say, find the 90% confidence level, or find the 95% confidence interval, or find the 99% confidence interval. Now, a couple key things to know as we move from that back to our paper. A couple other key things to know is the more confident, so to be more confident, and that can go down below because I wrote really big though. To be more confident, you will have a larger margin of error. Okay, so that's a key concept here. Is if the goal is obviously to have the most confidence possible, but to be more confident, you end up getting a larger margin of error. So like a good example that I usually use in the margin of error is if you take something very small like this, you could say like this little glass jar or whatever. If I sit this like on the ground and say, what's my chance of, just wait. If I take this on the ground, if I have a piece of paper, okay, and I say, how confident am I in throwing this piece of paper into that jar. I'm not going to be very confident, okay? It's a lower confidence level for me to throw this piece of paper in that jar. If I want to have a higher confidence level, if I want to be more confident in doing something, I've also got to have a bigger margin of error. So I'm a lot more confident that I can throw it in that trash can because I can miss and still hit the target, right? I can have a larger margin of error. I'm not as confident. That was pretty good, though. I'm not as confident that I can throw it in the jar because if I miss by just a little bit, then it's off, right? But I'm more confident I can throw it in the trash can. So that's what it means. The bigger the margin of error, that's how you get more confidence in it. But you also want your margin of error to be small. So it's both ways, right? You want your margin of error to be small because you want very accurate results, but you want to be very confident. And to be more confident requires a bigger margin of error. So you got to kind of meet in the middle. One other important thing on here is to be more accurate. So the way we can kind of combat that, we can be more confident, which means we have a larger margin of error. But to be more accurate, we can take a larger sample size. Okay? And we talked about that before. We'll just say take a larger sample. So the bigger this n is right here at the bottom, which is our sample size, the bigger the n is, the more accurate we're going to get in our sample. So that can kind of get rid of that large margin of error. So if I want to be like extremely confident, my margin of error is going to go up, so I need to increase my sample size to try to bring it back down and become more accurate. Okay. Remember, margin of error is just how far off it is each way. Okay, so these are the important things for a proportion. Now, at the end of these, so one last kind of, before we get into the problems, so you kind of know what you're dealing with. At the end of these, you are going to end up with a interval. It's going to be from the lower end to the upper end. Okay? That's going to be called your confidence interval. It's going to be, you're going to write it in a parentheses. It's going to be the lowest that it can go to the highest it can go. And what we're going to say when we get that interval, we have to write a conclusion. Our conclusion is going to be, we are, and it's going to be the same one every time, blank % confident that the true proportion of blank is contained in the interval between blank and blank. So there it is over there. So the way we'll finish up a interval is we'll get the actual interval. That'll come from the calculator. The calculator will give us the interval. We'll say we are blank percent. If it's 95%, then we're going to say we're 95% confident that the true proportion of people that enjoy music is contained in the interval between, and we'll take our lower number and our upper number. So we're going to say the same thing with every problem. We're just going to change the context of the problem. But that's a sentence you need to kind of memorize. So we are blank % confident that the true proportion of whatever the problem is contained in the interval between this and this. Now, when we're talking about proportions today. When we're talking about means later, we'll say we are blank % confident that the true mean is contained in the interval between there and there. So this sentence is going to help you no matter what interval we're talking about. When we start talking about two proportions, we'll say we are blank % confident that the difference in the two proportions is between blank and blank. So all that's going to happen. All right. What else? Let's see. For proportions, there's one maybe other key thing that you need to know before you can actually run an interval. Sometimes it says to check and I know we're running out of space here, but you want to check, there's 3 conditions that you have to know that are met before you can actually run the interval. This is going to happen with any test. So 3 conditions that have to be met. Number 1, it has to be random. Okay? So either randomly selected, randomly assigned, etc. Something. It has to be somehow the way they got their sample has to be random. Either they randomly picked people, or they randomly assigned people to different groups, or they did something. But it's got to be random. The next one is that it is independent. We'll talk about that in a second. And then the last one is that it is normal. Okay? Random, independent, and normal. Independent means, and I'll write this for later, to be independent, it means that our sample must be 10% or less of our population. Okay? Another way of writing that is that your population must be at least 10 times the size of your sample. So I've read it that way before too. Either way is fine. You either say your sample is 10% or less of your population, or you say that your population is at least 10 times the size of your sample. So think about it. For this school, if we had 800 students and our sample was 100, it would not be independent. Because 100 is more than 10% of our sample. Okay? So of our population, sorry. So 100. So for it to be independent here, if we have 800 students, we would have to only sample 80 or less to make sure that it's independent. Independent means you don't want one person's opinion or one person's answer to depend on the other. Independent's a good thing, right? Normal, you're going to use this. N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. You want to check those things off for it to be normal. Okay? N is your sample size, P is your probability. So think about it. It's basically saying you want a big sample size. For it to be normal, N times P has to be greater than or equal to 10, and N times 1 minus P has to be greater than or equal to 10. That's a lot of stuff here for beginning. But this is going to be the same conditions throughout, like for all the tests that we run.
Is this easier than last year?
Probably. Yes. So you got the random, independent, and normal. Before you can do any problem, you have to check those conditions. If you don't check those conditions and you just write down the answer, it's wrong. Okay. So I've had people, there's free response, these are good free response questions. There's people that have taken these free response questions, they saw that it was a 1 proportion. They went to their calculator, stat, test, 1 proportion, typed in the numbers, got the answer, wrote it down, they got a 0 for the exam or whatever it was, right? Because they did not check the conditions, they did not write the conclusion, they didn't set up the problem. You can't just throw out an answer to that. So these are your, so this is your introduction to a 1 proportion confidence interval, and now I'm going to show you 3 of those and how it works. So now you can kind of see how much work goes into one problem. So I don't think it's going to be, it shouldn't be overwhelming, but we'll see where it goes. This says, recently ACT Incorporated reported that 71.9% of the randomly selected college students in public colleges that were freshmen in 2010 returned to college in 2011 for their sophomore year. Estimate the national freshman to sophomore retention rate in colleges with a 95% confidence interval. Okay, so first of all, we're going to go to our conditions. And actually, I'm going to give you an acronym to remember all the things that you need to do for a confidence interval, okay? So anytime we get a confidence interval, we're going to say panic. Okay? So P stands for what is the parameter of interest. So the thing that we're interested in learning about is the ACT, the students that come back to college, that return to college, right? So return for sophomore year. And we get that in our sample, we have 363 out of 505, right? Which is, they say 0.719. That's your parameter of interest. That means, like, what are you interested in learning about? You're interested in learning about, like, the true proportion of people that return for their sophomore year. From this, we get a sample that says 363 out of 505 returned for their sophomore year. Okay? And we're talking about public colleges also, so that's important. And I'll say public college students. So there is a lot of writing in some of this too, yes. Now, A stands for your assumptions, which are the same as conditions. So that's another word for conditions. So assumptions. So there are 3 of them always. Number 1 is random. Okay? So random, it says it. If it says it in the problem, you just have to say it was randomly selected college students. So randomly selected college students. And put a check by it. So that shows that you know that it is random. You know that that condition has been fulfilled. You know that it's random. Okay. Number 2 is independent. Independent means, so there should be more than 5,050 college freshmen in public colleges. You think so?
Yes.
Yes, absolutely. Okay, now why did I pick 5,050? Because that's 10 times the size of my sample, right? So remember, the sample has to be 10% or less of the population. So that means the population has to be at least 10 times the size of my sample for it to be independent. So there are more than 10 times that many college freshmen in public colleges. Now, do I know exactly how many there are? No. But I assume that I know that that's a common fact. We know there's more than that many. So we don't have to know the exact number. We just know that it's a big number, right? So now we go to number 3, normal. For normal, n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. These are your successes and your failures. Now, you don't have to actually calculate it. You should get it from the problem. Successes are how many people actually return to college, which is how many?
360.
Yep, 363. That's greater than or equal to 10. You put a check by it. Failures are how many people did not return to college, and we have to figure out how many that is. That's, huh? Yeah, it's 505 minus 363, but we got to know the exact number. 142, yep. So, check. So, we got the 3 assumptions. It is random because there were randomly selected college students. It is independent because now we know the population's at least 10 times the size of our sample, and it is normal by a long shot. Those were much greater than 10. All right. N times P would be, here's what it would be. N is 505, okay? P is 0.719.
Oh.
If you do 505 times 0.719, you get this. And if you do 505 times 1 minus 0.719, you get this. So it's easier to just, if you already know how many successes you had, you put that there, and if you know how many failures you had, you put that there. Okay? So I basically saved you a little time of multiplying. Now, N is the name of the test. This is a 1 proportion. Let me spell it right. This is a 1 proportion Z interval, because that's the name of the test we're going to do on our calculator. Okay, so 1 proportion Z interval.
So if one of the conditions was, would they even give you a problem where one of the conditions was?
This can be the longest video. 1 proportion Z interval is the name. So Now we're going to actually find what is the interval. Okay, so we're going to use our calculator finally. So the interval, the interval is the formula you wrote down. So we actually could put in that whole formula, p hat plus or minus the z star, and you are going to have to know that formula. So, but your calculator will do that for you. So we're going to go to stat test, and we're going to go to the 1 proportion z interval. There it is, letter A. And it asks us what X is. X is how many successes we had. We had 363. N is how big our sample size is, and that was 505. And C level is what do we want our confidence level to be. We'll look at this when it says, estimate the national freshman to sophomore retention rate in colleges with a 95% confidence interval. So we want our confidence level to be 0.95, 95%. And we calculate. So that is our interval. Our interval is from 0.6796 to 0.75802. Now, if you're thinking about that, you're thinking we are 95% confident it's going to be somewhere between about 68% and 76%. If we kind of estimate those intervals, it's somewhere between close to 68 and close to 76. So that's our interval. Now we write our conclusion, which is that sentence. Okay, so we are 95% confident. This is where your writing comes in. That the true proportion of, and I usually look at the end of the problem. And you say, do you have to be that detailed? Yes. So that the true proportion of what? Well, there it is. National, look at the last sentence of the problem. National freshmen to sophomores retention in public colleges is between, or you could say is contained in the interval, either way, is between, and then I'll see in my two numbers, 0.6796 and 0.75802. There's my conclusion. So we are 95% confident that the true proportion of national freshmen to sophomores retention in public colleges is between 0.6796 and 0.75802. So that tells us we got about 72% retention rate in our sample, but we're 95% confident that the true retention rate is somewhere between 68 and 76, which means we have a little bit of margin of error because we're never going to be completely exactly correct. It could be a little bit off one way or the other. Paralyzed Veterans of America is a philanthropic organization that relies on contributions. They send free mailing labels and greeting cards to potential donors on their list and ask for voluntary contribution. To test the new campaign, they recently sent letters to a random sample of 100,000 potential donors. So the sample size is large, which means we're going to get a very accurate result, yes. And received 4,781 donations. Give a 95% confidence interval for the true proportion of those from their entire mailing list who may donate. So they have more than 100,000 on their mailing list. They probably have millions on there. Okay, but this is this is the sample that we got. So let's do this. Let's see how quickly we can go through this. So P is the parameter of interest. We're interested in the proportion from the mailing list who donate. Okay, and our sample, our P hat was 4781 out of 100,000. And you should actually be able to figure out what that is. That would be 0.04781, a little under 5% of that. So that's like our parameter of interest. That's what P stands for. What are you interested in and what do you know? That's what we know. That's what we're interested in. A are our assumptions. So number one is random. We have to look in the problem for that. Random sample of 100,000. Check. Number two is independent. So we have to assume there are more than what? Assume there are at least how many potential donors?
1 million.
Yeah. At least 1 million. If you want to write the word 1 million, that's fine. 1 million potential donors. It's got to be 10 times the size of our sample. Okay? Normal. It's obviously normal because it's really large, but we still have to write what makes it normal. NP is greater than or equal to 10. That would be your successes. That's 4,781. And N1 minus P is greater than or equal to 10. That's your failures. That would be 95,219. I think so. I subtracted from 100,000. All right. Okay. So those are your successes and failures. So you checked all your conditions. Those are your assumptions. You name your interval. This, again, is a 1 proportion. That's the easy part right now. But once we get a whole bunch of these, you'll have to think about it a little more. It's a 1 proportion Z interval. Notice with the Z, I always put that little line through it because it can look like a 2. So 1 proportion Z interval. The interval now, again, now this time, let me write it out just so you know what it is. And then I'll do it on the calculator. But you do need to know, I know that some of you are like, well, when are you going to use this? You do need to know the formula because multiple choice and other things are going to require you to. So the formula is 0.04781 plus or minus. What Z would we use?
0.95.
What Z score would we use? Look back at the Z's that on the first page. 95%. So what's the Z score for 95%? Yeah, 1.96.
How do you decide if it's plus or minus?
Time, it's always, you're going to do both. When you do a confidence interval, you add and subtract. That's how you get the lower and the upper. 1.96 times the square root of, and then we just put these in. P is 0.04781. 1 minus P, you can just put 1 minus 0.04781 over N is 100,000. So there you've wrote the formula, okay? Now you don't have to go work it out by hand, but sometimes they may want to see the formula. That just means, hey, I know where the numbers go. I know how to plug the numbers in. I know where they're supposed to be. I know what the calculator is doing when the calculator makes this interval. Okay, so it tells the person that you actually know a little bit more. You didn't just press a button on the calculator. Okay, now the final interval here, I never would want you to do all that by hand. That would be I'd be asking for a mistake. Okay, so you want to go to the calculator. You want to go to stat, and we'll go over to test, and we'll do the 1 proportion Z interval. Is it letter A for everybody?
Yeah.
I was just curious if it was the same on all of them. So 4,781 out of 100,000. Now, if you didn't know the decimal for some reason, out of 100,000 it was easy. But let's say you didn't know the decimal when you calculate it. You see how it gives you p hat? So if you didn't know the decimal, you could actually leave that blank in your parameter of interest and then come back and get it at the end. Like that, the decimal up there at the top. All right, so the interval is 0.04649 to 0.04913. Very accurate, right? It's only like just barely off. We know it's under 5%. So our conclusion is we are 95% confident that the true proportion of people who will donate from the mailing list of the VA, right, is between, and then we say our two numbers, 0.04649 and 0.04913. So with this information, I could pretty much tell you that the true proportion of people who are going to donate is going to be a little bit less than 5%. So if I send out 1 million letters, I can pretty much say probably about 40,000 people are going to donate. That's good. Right now, sending out 1 million letters is going to take a lot of time. But you can kind of see what you're going to get in responses. So like a similar thing could be like, let's say I'm a club at Lincoln or wherever, and I want to know how many businesses may donate to me if I just send out a letter. So I send out a letter to 50 local businesses, and I see how many donations I get. Okay, that could then tell me the true proportion of donations I'm expected to get. So I don't get my hopes up and think, oh, all of them are going to donate, or even maybe only 10 donate. Now I know maybe about 20% are going to donate. So like businesses are going to use this in order to see like how much money they're going to get, what kind of response they're going to get from people. Kind of like when they send out things about wanting you to subscribe to a magazine or something like that. How many people actually subscribe from those? Then they can kind of figure out how much money they make. So is it worth it to actually send those things out? Or should they send them out by email? Well, if they get the same subscriber rate by email as they do by paper, then I'm going to go with email because email is free and paper costs money to do the stamps. So like that's where you start thinking about these things, and the statistics actually make sense in like a real world setting. So it's going to make sense for a company to look at these statistics. That's why they're hiring people to do things like that. It just says a National Health Organization warns that 30% of middle school students nationwide have been drunk. Okay. Concerned, a local health agency randomly and anonymously surveys 110 of the 1,212 middle school students. So we actually know how big our population is here. It's 1,212 in the city. Only 21 of them report having been drunk. So 21 out of that 110. That's our p-hat. That's our proportion. Give a 95% confidence interval for the true proportion of those who report having been drunk. And we're talking about middle school students in this city or now work. So let's go over this one. The parameter of interest is we're interested in the proportion of middle school students in the city that report being drunk, right? And there are 21 out of 110. What was that decimal?
0.1909.
0.1909. Okay. All right, so the assumptions, number one is that it is random, okay, and it says it, randomly surveys. So I'm going to put a check. Number two is that it is independent. So we say there are more than 1,100 students in the city, and there are, because there are 1,212. Number three is that it is normal. So N times P is greater than or equal to 10. That's 21 is greater than or equal to 10. What's N times 1 minus P? So how many failures were there?
89.
89. Yes. Is greater than or equal to 10. So we checked both of those off. So we got both of those. And then we're going to go through N, which is the name. Again, 1 proportion Z interval, the easiest part right now. We're going to get the interval from the calculator and then write our conclusions. Again, to get the interval from the calculator, we'll do it one more time. This one won't be as accurate, right? Because we only had a sample of 110 instead of a sample of like 100,000 in that last one. So 1 proportion Z interval, we have 21 successes and 110 in our sample size, 95%. We're going to calculate it. We get from 0.11746, so almost 11%, all the way up to 0.26435. So you see it's not very accurate. So we are 95% confident that the true proportion of middle school students in the city that report being drunk is between 0.11746 and 0.26435. And see, that's a wide range there. So it's somewhere between 11 and 26%. So that's not really giving us great data. And the reason is, again, because we only sampled 110 of them. See how accurate we were when we had 100,000. Now, you want somewhere, those are extremes. Somewhere in between would be nice. You want a big sample that allows you to be accurate, but if it's too big of a sample, it's going to be too time consuming, and it's not going to be worth your time to make it more accurate, okay? So that's the other issue that you have as you go through this process. Okay, so that is the 5 for that problem, and then I'm going to give you the last problem that I'd like for you to do today, so I'll move it up here. So the last problem for you to do on your own, you can put it at the bottom of that sheet and turn in with it, or however you want to turn it in. It says, I'll read it and then I'll leave you alone for this. If 320 of a sample of 550 people leaving a shopping mall claim to have spent over $25, determine a 99%, so be very careful when you're putting this in the calculator. You're going to change your confidence level for the first time today. A 99% confidence interval for the proportion of shopping mall customers who spend over $25. So we know that 320 out of 550 spend over $25. We want a 99% interval to estimate that proportion. And you're going to do PANIC, P-A-N-I-C. Parameter of interest, what do we know? The 3 assumptions, the 3 conditions, the name of the interval, the actual interval, and then your conclusion. And then you'll turn that in with the rest of this for today.